Again, let me tell you what we did. We go through the low frequency, in which we can short the large capacitor. Okay, but for some capacitor we put there, we still need to take into account. And then eventually we got to mid-band, all the capacitor can be shorter. So that is the regular circuit we learned in the first part of this class. But then we go to even higher frequency. The parasitic capacitor of the transistor will have effect. Then you will create poles. And that is where our circuit fails, right? So let's take a look at this one again. This is a common gate amplifier. Why it is a common gate? The gate is grounded, right? The AC grounded, constantly DC bias. And the input is to the source, output is at the drain, so it is common gate. Of course, you will say, compared to what you learned at the very beginning of the class, you have an extra current source. You also have a CI and RS. We do this for biasing, right? Because we cannot just apply the small signal model to small signal to here. We need to bias the circuit so that it is in which mode? Saturation, right? That's why we need this I. And we cannot mess up the DC voltage and the AC signal. So we have a capacitor, which is open for the DC voltage or current, but it is short for the small signal or low impedance for the small signal, right? So that's why we have this circuit, right? For example, let's say this is biased at 1 milliampere, right? And then maybe this output is at 3 volts. And then I try to have some tiny input, maybe 10 millivolts. Then this will fluctuate. And then eventually this one becomes maybe plus minus, at plus minus, for example, 0.1 volt as the gain. Of course, this is a common source. It has a gain, right? I spent a lot of time discuss this before about the small signal model. I hope that you understand this. So, okay, but now we need to go to the frequency domain. This is the given circuit. I cannot take away RS and CI because it's in the AC domain. I need to take them into account. What is the gain of this circuit? How would you approach it? The first thing is definition. What is the meaning of gain of a circuit if I give you? Very trivial, but I want you to be able to write it down confidently. What is the gain of the circuit? By definition, I'm not asking you for the result. Yes, right? Very simple thing. But do you know what is V out of V over V in by inspection? No, right? But you probably will, for those who did study, you probably should have found as already grumbling, saying that, oh, it's because of something. Otherwise, I would already know how to do it. You already know a part of it. What is the gain that you know already from this circuit? If I call this V, this point X. You already know what is V out over Vx because you did the small signal derivation before, KCL and KVL, right? So that's why you say, okay, I'm going to do it in 2 steps. But giving me V out over Vx is useless because I also want to know V out over V in, right? So you also need to know Vx over V, good, right? Just a chain rule, right? This is something you want to use in the future also. For voltage, you can do that, right? For current, it's different. So V out over Vx is easy. V out over Vx is just the A of common gate. And what is that? Remember? GM-RD. Very good. Common source is negative GM-RD, right? Common gate is GM-RD. So you've done most of them. Then how about Vx over Vi? We have tried this before, right? What we will try? This looks like a what? Voltage divider, right? So just treat you as an electron. So I go in from here, we in. Rs, I have Ci, And then when I look down to the current source, what impedance do I see? Infinite, because it's ideal. And then what else? I can look up. When I look up, what is it? 1 over Gm. So he answered all the question, right? Can you, anyone has questions to him? Huh? Yes, 1 over Gm, sorry. 1 over Gm. Looking up is 1 over Gm. Just exactly what we did earlier. Here. Isn't that we were talking about this? Looking up is 1 over Gm. Because the gate is constantly biased, so it's AC ground, you look into the source. When you have enough channel, your channel length modulation is not serious, or your RL is large enough. RL has no effect, right? Same here. We're looking up, right? Oh.
They finally found their checkbox. They have to check that says -7. Drop that box. It's always getting hidden in the menus. All one-page menus.
So there might be some,
Good to have that.
yeah.
Willing endorse on that.
Okay, what are I talking about? Yeah, so that's it. Is that okay? So this is x, right? Now it is easy. What is Vx divided by Vi? 1 over Gm divided by everything, right? Rs plus 1 over Sci plus 1 over Gm. Okay? And do I assume anything? Actually, I don't. So this is equals to, I'm going to multiply everything to the top. I get Sci. I still keep 1 over Gm. Okay? And then I will get 1 plus Sci times Rs plus 1 over Gm for some reason, right? So what I'm doing is just multiply Sci to the numerator and denominator, so this become 1, right? And then these two terms add together times Sci. The reason is that I want to find the pole, and it's very clear what is the pole. So P, of course, the total gain is going to be GMRD times this one, right? So, but the first one doesn't have pole, right? So pole equals to 1 over Ci Rs plus 1 over Gm. That's what we get by doing this, right? Maybe I should also write down the total gain, right? It's just total gain. Oh yeah, you can put that. Yeah, let me fix that. Total gain, of course, then equals to, this is not good color, SCIRD, right? Because GMRD times this one divided by 1 plus SCI RS plus 1 over G. Right? Because the total gain is equal to GMRD times this one. GM got cancelled, then I have SCIRD times this whole thing, right? And then I have this denominator, and he said that I should put a negative to be accurate, which is correct. Okay, now, so let me do this. This is 3, and then we have 4, right? I just keep doing this, and then 5. So when we plot it, we know that I have a 0 at 0. Do you see that? SC1. So you keep going up from negative infinity. Log 0 with negative infinity. And then eventually, it will hit the pole. And this pole is P1. Okay? So it's very similar to other architecture or the common source, right? You always have something like this. Because, of course, because when you are DC, if your input is DC, you cannot go full CI. You cannot get any signal into this circuit. There's no amplification. Only when you are larger than the pole, which is about RSCI, that means that you are really, this is short circuit, right? And then you will get the signal into it. And then the gain will be close to GMRD. Okay? So as we discussed, then what happened at mid-band, right? You keep increasing. So we can look at two methods. They are actually just the same. We study when omega is much larger than P1. Okay, when the frequency is much larger than P1, right? Then if we copy the equation from before, you see Vx divided by Vin, as I said earlier, is SCI 1 over GM divided by 1 plus SCI Rs plus 1 over GM. Right, the pole is negative 1 over CI Rs plus 1 over GM, right? So when the frequency is really large, then the 1 can be ignored, right? 1 can be ignored when you have a very large frequency, when your frequency is much larger than P1. Is this okay? Then with that, SCI got cancelled, right? Then you have 1 divided by 1 plus GM Rs. Okay, for this part. But then for V out divided by V in is equal to GM RD. You have GM RD, right? From the V out divided by Vx divided by 1 plus GM Rs. So this one is not GMRD, it's GMRS, which is similar to what? Do you remember this equation? Do you recall? Ring the bell? Looks like what? Do you remember? The exam problem. Correct. Like the exam problem. What was the circuit in the exam problem? What circuit, what amplifier was that in the exam problem? He said this one looks like the exam problem. So what circuit was that? Like source follower, that's what I said was or the gain is like common source with degeneration. The gain of this circuit is like this. If I have RD and I have RS, the gain is approximately equal to GMRD divided by 1 plus GMRS, right? And why we have RS? Because I have a source resistance from the source, which is usually small. If it is small, then this is just GMRD, which makes sense. When I am at high frequency, C1 is shorter. And if RS is small, then Vin is just like applying to the source directly. And that is just a gain of a common gate amplifier, right? So it's GMRD. So this is one thing, right? Another method is like this. It's not really just another view, right? We can claim that, well, when I design the circuit at mid-band, CI is shorter. It is exactly the same as what we are assuming here. When the frequency is high enough, this is shorter, okay? Yeah, and then this is just like what do I say this? Then you need to go through the potential divider, right? You go through the potential divider, Vx. What I'm doing is basically just repeating what this is x, right? Equals to 1 over gm divided by 1 over gm plus rs, which is just equal to 1 over 1 plus gm rs, right? So you get the same thing. Okay, this is not really two different methods, but this is easier because if I see that it is shorter, I just can do this Vx. So this is Vx times V in. Okay. Any questions? Right, so with this, then now I know what my Bode plots look like. It is like this. So it has 0, it hits the pole 1 that we studied in the last slide, and then its gain is Gm Rd divided by 1 plus Gm Rs. Okay. Then I want to look at the high frequency response, right? Because now I keep asking, what if you keep going to higher frequency? Eventually, what happened to the gain? In this case, I need to draw the capacitors. So here, where is my Ci, however? Isn't there have a Ci here before? Yeah, I shorted it, right? Because even at mid-band, I already short it. Now you are at even higher frequency, then of course it is still shorted, right? 1 over omega C is the impedance, right? Now the omega is even higher than it is shorted. Then I have 4 capacitors, right? So I'm going to simplify the circuit. How can I simplify? The first thing is this is grounded, right? So if I look at this, I will get this. V in, right? How can I simplify it? Any idea? Okay, he start with this. He said he claimed that this is like this. CDB plus CGD. Do you agree? Yeah, because they have the same terminal. They both connected to Y and the other terminal connected to ground. Again, this is AC ground, although it's DC bias, right? So how about for the other two? It's the same, CGS plus CSB. Very simple. This circuit, no Mueller cap, very simple. So what are the poles? I have an input pole. What is that? We even don't want to spend time to trace elevator and stairs. You probably can tell me right away. What is the pole for the input? 1 over Rs times CGS plus CSB. Is that all? Then let's go back to the elevator and stairs. If you stand here, right, you still have 1 over GM. So be very careful. So it's Rs parallel 1 over, should have saved enough space. Rs parallel 1 over GM. Right? Again, I stand here, I ask myself, what are the resistive path that brings me to the ground? Going up is 1 over GM. I'm going to the source. Here, I need to ground V in, right, in principle, because it is an independent source. So maybe I should make it more explicit, right? So it's Rs parallel 1 over GM. And then what is the capacitor that can bring me to the ground? CGS plus CSB. Now, how about the output pole? Actually, I want to do one more simplification. So usually RS is small because it's the source resistance. If you have a good source, you assume you make it small. So this is approximately equal to G 1 over GM. And usually SB is smaller than GS, as I showed you earlier in the cross section, right? Because source to body, particularly in FinFET or SOI, SB is very tiny. Okay, so this becomes CGS, which approximates equal to GM divided by CGS. Okay, this is very interesting. How about the output pole? What is that? Assume no channel length modulation. 1 over RD. Thank you. 1 over RD CDB plus CGD. CGD small, usually. Do you remember what CGD? Let's take a look at the cross section of a transistor again. Yes. Very good. It is the tiny overlap between the gate and drain, so it is small. Yeah. No, it's just the process you are going to have overlap in the old time, the diffusion process. Otherwise, you will get disconnected. Right? If it's outside underlap, then you have a very resistive area. Yeah, so usually it's a little bit overlap. So what is the point? Here is usually P out is larger than P in, so which is okay. So let's look at this. This is the Bode plot we have for common gates amplifier. It's 0, hits pole 1, become constant GMRD, and then you hit P in and P out. Okay, what is P in? Anyone remember this expression? GM divided by CGS. P in GM divided by CGS is just equal to the transit frequency. The fastest your transistor can operate. Remember, we spent that. It is when the gain equals current gain equal to 1 at that frequency. So your transit frequency may be 50 gigahertz, 100 gigahertz. Your circuit cannot operate faster than your transit frequency, right? Just as I said, if your building is just a matter of stacking up the brick, and then the per unit area you can stand, the force per unit area you can stand cannot be larger than the brick that you can, right? Same for this one. So common source, common gates amplifier, it rarely creates a bottleneck in your circuit because it's really fast. It does not have Muller capacitor, and its pole is like at the transit frequency, in the order of the transit frequency, right? So this is another advantage of using common gates amplifier, right? So at the beginning, say common gate and common source looks like the same. Yeah, they are inverted. One is positive gain, one is negative gain, and then they both have a large output impedance. Now, from the equal frequency domain, you see their difference, right? So now you grow up, you know many things. So if you go to the industry, when people talk about the circuit, we don't only look at the DC and don't only look at the gain. Now you know very well I need to consider what is the input impedance, what's the output impedance, whether it's positive or negative gain. And then, of course, the power consumption, is it easy to lay out? And then its frequency response. So all of them have their pros and cons, and you need to pick the right one, right? If one is always better than other, they would have been eliminated from the test book. right? Razar, we won't put this in the textbook. So remember this. So even you don't understand why something exists, it's just because the limitation of our knowledge. They exist for some reason, right? So we also have like diversity in engineering, no kidding, right? In the circuit. Okay, the last thing we want to study is the source follower, but it is very easy because it's very difficult. The reason is this. For source follower, again, you have 4 capacitors. And you will see that this capacitor is giving us trouble because it doesn't have any terminal connected to the ground, right? So you will try to apply Mueller effect. And that's what I put in the question 1 in the midterm, right? Which is okay when you do that in midterm. But in reality, this won't work because this is a very strong coupling between these 2 nodes. And as you can see, you are going to get 1 minus A equal to 0. Because in ideal case, because source follower has a gain of 1. That also doesn't make sense already, right? So anyway, the only message here is that in some circuits, you cannot apply the Mueller effect because there's a very strong coupling. The theory will not work. So many things you learn in the school actually will break down in the reality, right? So besides knowing how to use it, most important thing is be ready to recognize that they won't work. Okay, so in that case, you need to solve KCL and KVL and come up with this equation and then find the poles. So here definitely you can use the dominance pole approximation to help you to check if you can get it easily. Okay, and that's all I want to say about source follower. Okay, so we are done with the frequency response. Now we will go to feedback. And before that, I want to remind you some of the very fundamental concepts, which are very important concepts actually, can gauge whether you really understand electrical engineering.